deviation be corrected by posture stabilizing mechanism in the dashed posture as compared to solid line posture? And the answer is yes and no. Yes, if the deviation is produced by an external perturbation. So if somebody comes from the back to me and pushes me a little bit, I will have a reaction that's involuntary, that's mostly spinal and, well, maybe brain stem involving, but very quick reaction, stabilizing posture. However, if I do it myself, there is no such a reaction. What happened? How come that I can deviate my posture without triggering the action of posture stabilizing mechanisms, which are supposed to be very peripheral, reflex, kind of spinal? So what happened to them? Are they suddenly turned off? Well, to me, this is a very important, it's kind of a trivial example, but it's a very important example when one thinks about different hypotheses on the control of movement and posture. Now, I'm a big fan of the equilibrium point hypothesis, and I'll explain you why in a second probably. Now, equilibrium point hypothesis says that any kind of a movement is a shift of the reference frame, a reference frame. If you shift a reference frame, then your current state is a deviation from the newly defined state, and forces may be generated that will move you to the new state. Okay? Posture stabilizing mechanisms, according to the equilibrium point hypothesis, become movement producing ones. So if this is my posture being stabilized, then any kind of deviation produces posture stabilizing mechanism bringing me back to this posture. If this is my posture being stabilized, even if somebody pushes me towards vertical posture, which is more stable, I will have a response leading me back to this less natural posture, leaning forward. Other hypotheses say that maybe posture stabilizing mechanisms are turned off, or there are other forces to counteract them. These are all very unreasonable arguments, because it's very easy to show examples that it simply doesn't work like that. So let me now introduce to you the equilibrium point hypothesis in a very general way. So first we start with a single muscle. And this picture shows the relation between active muscle force and muscle length. This is tonic stretch reflex. Basically, this is the characteristic of the tonic stretch reflex. It usually starts at a certain value of muscle length that's shown here as lambda, until for muscles shorter than lambda there is no muscle activation, and muscle resists stretch only passively due to passive elastic properties of the muscle and tendon, and I'm not even showing it here because it's very small force. Starting from lambda, if you continue stretching the muscle, it will generate EMG, it will generate activity, and it will be higher and higher when you stretch it more and more. If there is an external load corresponding to this value of muscle force, there is going to be an equilibrium point for the system muscle plus load plus all the reflexes, which is shown here as an equilibrium point. And that's the only point when where the system is in an equilibrium. Now, if you deviate by a transient force, you take it and deviate from the equilibrium state and let it go, it will come back. Because that's the only equilibrium existing for the system, just don't have choice. So small perturbations lead to what's sometimes called equifinality. So if there is a small transient perturbation, the system comes back. Now, what happens during voluntary movement? You start from absolutely the same situation. There is an equilibrium point, a state of the system. Now, you change voluntarily the threshold of the tonic stretch reflex. You shift your characteristic to a new position, from lambda 1 to lambda 2. What happens now? Equilibrium point 1 disappears. It's not equilibrium anymore, because that characteristic doesn't exist. And point 1 becomes a deviation from the only new equilibrium point, which is shown here as a red dot, equilibrium point 2. And the system will move there. So posture stabilizing mechanisms and movement producing mechanisms are the same. They all result from shifts in the referent position for the muscle, referent length of the muscle. It's being produced by changes in the subthreshold depolarization of corresponding motor neuronal pools, but I'm not going to go into that today because otherwise it will take too much time, and it is already taking quite some time. Tonic stretch reflex, by the way, is a very interesting example of a synergy. It's probably the most common synergy we have in our body. So here is the system. The tonic stretch reflex characteristic and how it comes about. So there is the muscle, there are length sensitive, velocity sensitive, and other things sensitive receptors sitting in the muscle, but let's consider length sensitive for now, muscle spindles that produce basically positive excitatory effects on the alpha motor neurons, which is tonic stretch reflex. Now the lambda is our command, and let's assume that it's fixed, so it's not changing. Imagine the following. Imagine that one of the motor units suddenly turns off. So out of those 3 motor units, the central one, for whatever reason, decides not to work. Well, the amount of excitation the muscle receives will become smaller. The muscle force will drop. Now, the load applied to the muscle will be larger than muscle force, and the load will stretch the muscle. If the load will stretch the muscle, the efferents will feel that stretch, the spindles will fire more, and they will produce more excitation to the remaining motor units. So you will, if you record the outputs of individual motor units, you will find this wonderful negative correlation. If one motor unit fires less, the others, through the mechanism of the tonic stretch reflex, will fire more. They will compensate for each other errors. So one can view tonic stretch reflex as a mechanism stabilizing the equilibrium point, the equilibrium state of the system. Actually, it doesn't matter what is on the axis. I think it's a general rule that in our body, the amount of active force produced is proportional, no more or less proportional, to the distance between the referent coordinates of the object you are studying and its actual coordinates. Now when people study gripping, they usually analyze normal forces that are produced. But what's actually produced? What am I telling my fingers to do when I grip this object? Well, very easy to find out, just take the object out. And my fingers move to their new equilibrium position. So when I'm producing force, I'm actually changing the referent coordinate of my thumb and my index finger, or the referent aperture between the 2 fingers, to a new value. And the distance between the referent aperture and the actual one is producing action, is producing active force production. So the system tries to get to its referent configuration where all the muscles will be at their threshold for activation, and the system will show minimal activity, minimal muscle activity. So again, you take it out and you see that the fingers move towards each other. The rigid walls of the object do not allow this to happen. That's why active force production takes place. Okay, so that's what is known now as a referent configuration hypothesis, that neural signals, which are associated with subthreshold depolarization of corresponding pools, also define referent values for salient task-specific variables, what we care about. And then there is a cascade of few to many transformations. Because, for example, if I want to move my fingertip, I need to, I control with my fingertip. But it needs to be realized by certain joint rotation. Certain joint rotations have to be realized by changes in muscle activations. Muscle activations have to be realized by changes in the firing patterns of motor units. So forth. So there is a cascade of those transformations when the input is relatively low dimensional and the output is relatively large dimensional. That's where this scheme merges with the idea of synergies, because at each of these stages there are quick feedback loops, or likely to be quick feedback loops, making sure that there is a synergic way of involvement of elements that stabilizes their total output defined by the input that they receive. So this is a very busy picture, but it kind of puts everything together. So it is drawn for the multi-finger action. There is a task that defines subthreshold depolarization of that neuronal pool N1, which projects onto a redundant set of neurons that will define referent configurations for individual digits, and there is a quick back coupling from that. Then they project on individual muscle referent values, which are lambdas, which are thresholds for tonic stretch reflex, which is also few to many, or one to many, and then each muscle has a lot of motor units. And the variable that's being produced by the task is associated, given the external force field, with the referent coordinate for the referent position for those important variables, just like referent coordinates of the fingers. When the two becomes the same, when the referent coordinate and the actual coordinate becomes the same, then all the feedback stop working. And since the input from the task is subthreshold, the neuron stops firing, and this whole system comes to a steady state, to an equilibrium, to the rest. So this system will continue functioning, and no, it doesn't matter how, but the exact patterns of involvement are not prescribed. But the system will continue functioning as long as the referent configuration differs from the actual configuration, and it will always be drawn to the referent one. It's like you're driving a donkey with a carrot on the stick. The carrot is your salient variable. You're not telling the donkey how to move individual legs. The donkey will do that for you. But by moving the carrot, you're moving the referent configuration, the referent coordinate for the donkey, and then everything else will happen. There is going to be this cascade of transformations. So the donkey wants to move there, so it moves legs, it moves joints, muscle activations change, and all those things. But it's not being computed by anything in any sense. It's just behavior of a very large physical system, very large and complexly wired physical system. Okay. All right, I think you're tired enough. So this is my current lab. No American names, as you can see. On the top, there are flags of the countries that are currently being represented in the lab. This is actually before my group merged with Zetsorsky's group. It's going to be a much more complicated slide next time, because now we have also representatives of a few more countries. So Vladimir Zetsorsky is the person with whom I work on virtually everything. And thank you very much. And by the way, before I ask for questions, one thing I learned in America, you have to advertise. So this is the book that was published last year in July. It's called Fundamentals of Motor Control. And basically everything you wanted to know about motor control but were afraid to ask. All right, questions from those who are alive.
Antoine? When you are studying the synergies, you obtain variability in the weight of the muscle, but how is it possible to take into account the maximal force that can produce each muscle? Because if you obtain high variability in the TFL, which is a very small muscle, you will not produce the same.
Yeah, okay, sure. Okay, I understand the question. All right, so there are two questions in it. One is the issue of normalization, and the second one is the issue of the defining the Jacobian. Now, the issue of normalization, we usually normalize all muscle activations in one of the two ways. One is we normalize them by the highest level of activity across all the tasks that the person performs within one experiment. So anything. So since all the tasks usually belong to the same class, we basically say, okay, so this muscle that's these muscles' typical involvement in all the class, all these actions. Or we do it by a standard action. So, for example, we ask people to hold a standard load in front of the body and in the back of the body through pulleys, in the right hand and in the left hand. And then the maximal activation across all 4 combinations of a muscle would be taken as 4 normalization values. So that's how we kind of equalize them. But then, when we do the analysis of synergies, we define the Jacobian using multiple linear regression. So multiple linear regression makes sure that all the contribution of muscles is measured in a way in millimeters of shifts of the center of pressure. So how effective they are to shift the center of pressure of the standing person. Because when we ask a person to do, I don't know, any kind of a task, and then I record all the muscles, and I record shifts of the center of pressure. Well, first we unite muscles into modes after normalization, as I mentioned. But then each mode is regressed. I mean, all the modes are regressed against shifts of the center of pressure, and then the gains is another normalization. So each mode is measured in centimeters of shifts of the center of pressure. Yeah, Julien.
Yeah, about the equilibrium point hypothesis, it goes with the toe hypothesis, since the idea is that it fills a gap that could be any dimension, meter or time or something. And in the equilibrium point, you have the reference configuration and the other one that have to merge or...
So one more time, because in the reference configuration hypothesis, reference configurations are measured in meters. These are real coordinates. Yes, the real geometric configuration. Well, can be angular movements, but it's all kinematic variables.
Okay, but the idea, as far as I get it, of the equilibrium point is that you have a configuration and you want to go to a new one.
Yeah.
And in the toe hypothesis,
in which one?
The toe hypothesis. Toe, the alpha.
Torque control, you mean?
No, not torque control, TAU.
Tau hypothesis. Oh, okay. Yeah, sorry.
I'm starting to look at that, so I want to understand a little bit more. In the tau, the idea is to fill a gap between two configurations also.
Well, the tau hypothesis asks, I think they are formulated at different levels of analysis of the system. The equilibrium point hypothesis is a very low level of analysis. It simply tries to link forces and displacements of the human system to potential neurophysiological variables that are producing them. Now, how you manipulate your reference configuration based on the task is done at a higher level, which is currently beyond my comprehension. I don't know. So, yes, according to tau hypothesis, you are estimating the time to contact, and then based on that, you start to shift your reference configuration in anticipation of something, which is fine. I mean, how you measure time, I don't know. I have no idea. So I think this question is to psychologists and philosophers, the second part. Yes?
Thank you very much for this talk. About the fatigue, you showed us some results about an increase of variability, good variability, with pre-fatigue of the index muscle. Have you got some data about what happened when the subject has to maintain a great muscle level of force, and when the fatigue occurred during the task? Is there an increase in variability?
Well, there is an increase in, because during fatigue, since we fatigue only one element, just by definition, during fatigue we can observe forces of only one element. Yes, it goes up. Variability goes up just as in dozens of studies before us. Because then when we look at the increase in good variability, it's done at submaximal levels of force and comfortable levels of force, and it is done by all elements together, fatigued and non-fatigued. So I think that your question has two components to it. So one of them I just addressed, but the other one is more subtle. How can you study these things, not across repetitive trials, but a long time? So basically, can you study indices of synergies within one trial, a long time? And this is a very interesting question. We haven't been able, we've been trying over the past 10 or 15 years, we've been trying to develop a method which we call in our lab in jargon, one trial UCM. Can you do it within a trial? Well, there are several problems. One is that the Jacobian may change. Then you cannot really compare data in one portion of the trial to data in another portion of the trial. But even if the Jacobian of the system remains constant, there is another problem, which is non-independence of observations. Now, all the indices that I've been describing to you, they're based on analysis of variance, basically. So linear statistical analysis. However, if you have a time series, it's a non-independent observation. So you just cannot do this type of analysis. So when people, we sometimes see it with the naked eye, that one finger force goes up, other finger forces go down at the same time during like constant force production. Constant steady state force production is probably the easiest example when one can do it. We once did it with John Scholz, because when we studied people with Down syndrome, and people with Down syndrome, they cannot produce many trials consistently. So we had to invent a method of estimating their multi-digit synergies based on very few trials. And then we developed a method, and it kind of worked. But now we realize that that was a very special case of a very special task when this method could be applied. All our attempts so far to generalize it and to make it applicable to all the tasks which we now analyze using the regular methods available, they've failed. So, so far, unfortunately, there is no single trial analysis method that would be analogous to uncontrolled manifold analysis of synergies, unfortunately. Because of those two main reasons, non-independence of observations and changes in the Jacobian during the time of observation. Then we don't know how to compare the data.
You described the effect of the fatigue on the motor synergy, but you don't make the difference between central fatigue or peripheral fatigue. What is your opinion on the potential effect or different effect between central fatigue and peripheral fatigue on the stability of the muscular synergy?
Another good question. I don't have a straightforward answer. Well, synergic adjustments are central, are neural. They cannot happen in the muscle, as far as we understand them now. So, but whether adjustments are neural to neural causes caused by fatigue or to peripheral causes caused by fatigue, I'm not sure, and I'm not sure that it would be very easy to distinguish, because you cannot cut the system into pieces. So even if you produce fatigue by direct electrical stimulation of the muscle, the sensory receptors will feel it, and there will be secondary effects in the central nervous system. Even if you don't see them, they may be diffuse, but they are there. So unless you dear-friend the person and you stimulate the muscle, and the person doesn't know, but if you dear-friend the person, then there may be no synergies to start with because of that. I kind of appreciate the question, but I don't think that currently we can experimentally cut the system into peripheral and central part cleanly enough to answer the question.
You showed some results concerning maybe 2 fingers or 3 or 4 fingers. And did you have some data? Do you have some data concerning bilateral coordination?
Oh yeah, this is very interesting. Okay, that was one of the most surprising results in our lab at first, you know that the greatness of a scientist is measured by the amount of time by which this scientist stopped progress in his area. So I got to 6 months when my graduate student discovered something, and I didn't believe her for about 6 months and insisted that she repeated the experiment again and again. So we saw a lot of synergies, stabilizing force during simple steady state force production. And then I asked her to do this task with these 4 fingers: press and produce total force. And then I wanted to see what happens within a hand. Fingers. So this is a typical hierarchical system. On the one hand, you first share the task between the 2 hands, but within each hand you share the task between the 2 fingers. So the result is the following. If I do the task with only one hand, there is a very strong synergy between the 2 fingers stabilizing total force. As soon as I add this hand, this synergy is gone completely. It's not there. But there is a very nice synergy between the hands stabilizing total force. Okay, so yes, we do study bilateral things. We, by the way, also ran a study which I didn't mention today because of time reasons. There is a study of fatigue which was published only, I don't know, a few months ago, when we fatigued one finger and used this task. And we looked at adaptive changes within a hand, within the other hand, and between the hands. And it's not a simple story. But it's logical. Everything, after you get the results, you realize that yes, it makes sense. But we couldn't guess it before we got the results. So this effect that in 2-finger task, the within a hand synergies are gone, was a big surprise to us. Then when we started to think, we realized that we should have guessed. Okay, I'm trying to figure out whether I can have the blackboard or the whiteboard. Well, if I can somehow get the whiteboard, I will explain you very easily and quickly how it happens, why this synergy disappears. But now, okay, thank you very much. So, this is force of one finger and force of the second finger within, for example, the right hand. Okay? Now let's imagine that you have a synergy. Well, no. Okay. All right. Force of the right hand and force of the left hand. And the task is to produce a constant force of the 2. Well, this is the uncontrolled manifold for that task, or the good variability subspace. And let's imagine that you have a nice synergy stabilizing it. So this is the data distribution. All right? So virtually all the variability is along the null space in this picture. All right. Let's project this ellipse onto this axis, on the left-hand axis. This is variance of the left hand, force produced by the left hand. This variance is more or less proportional to good variability, because it's basically this angle, good variability, multiplied by cosine of that angle. Okay? Now, let's draw the left-hand picture. So this is left hand. Force of the index finger and force of the middle finger. Same thing. This is the uncontrolled manifold, or the null space for the correct force production. But variance of the left hand total is by definition bad. So this thing is that. In order to have a synergy here, you have to have a monstrous ellipse like that. Maybe even going to negative forces, which is impossible. So, there is a trade-off. It's not absolute. You can have synergies on both levels. You can note that the notion of synergy only depends on the relative amounts of variance, not absolute amounts. So you may have a tiny ellipse here, nice and tiny, then here it's going to be like that. So this is possible, but the system has to want it, really want it. So in kind of non-ecological tasks like pressing with two hands, the system doesn't care. So as a result, it has a very nice synergy at the upper level of this hierarchy and no synergy at the lower level. So the actual data distribution looks like that. When you look into the experiment. Now, if you do the task of this type, holding an object, this is also a hierarchical system because your thumb acts against four fingers combined, virtual finger, kind of. And now the action of the virtual finger is shared among the actual fingers. In this situation, there is no synergy stabilizing normal force, but there is a synergy stabilizing tangential force. Well, one can explain why it is because when you analyze the biomechanics of the task and you realize what's going on with rotational equilibrium. So because some forces are more important for rotational equilibrium than others. But that's kind of beyond the story. So again, we do study bilateral actions. They lead to some non-trivial results. We do also study dominance in bilateral actions, like difference between the right hand and the left hand, partly in collaborations with Bob Sandberg, who likes studying right-handers and left-handers, but it's a long story. Yes.
New experiments. Are there some difference between tasks when you manipulate the force or the torque, or when you manipulate the displacement or the position?
Well, it depends on the task. I mean, we do study kinematic tasks when there is displacement, when there is action. We have studies of ranges of tasks. So, but during manipulation tasks, we usually would study kinematics. We would study joint configuration synergies with respect to the endpoint orientation or location, while during kinetic tasks we would study forces of individual digits with respect to total resultant force and resultant moment of force. Or am I missing something?
Do you think that the way that used by the central nervous system to produce the is different?
Well, according to the equilibrium point hypothesis, which is the only sensible approach in my opinion, to movements, force production and movement are absolutely the same results. They're results of they're different results of the same neural process. Basically, if I press on my hand, I produce force. If I remove hand, there will be movement. So if there is a stop, I cannot move through, I produce force. So basically, what happens when I press? I simply change my reference configuration. If there is no resistance, I go to that reference configuration. So force production and displacement, to me, are different peripheral consequences of the same neural process, including synergies.
Mark, may I ask about this four fingers stuff?
Sure.
So when you do this experiment, then there are four forces, right?
Yes.
And so you said that there is covariance between the force of one head which is the sum of the forces of two fingers.
Yes.
They call them fingers 1, 2, and then there are fingers 3 and 4.
Mm-hmm.
So there is covariance between the sums F1
Yes.
and F2, and on the other hand,
Yes.
there is also on the other hand F3 plus F4.
That's right.
Now, if you would study the covariance between the sums F1 plus F3, and on the other hand F2 plus F4, would you find one?
Well, I suspect that I will find something. I may find something because it's going to be a little bit. I think it's going to be a spurious result because since at the level of all 4 fingers there is a covariance. If you simply put together all 4 fingers, but simply the covariance matrix is such that these 2 covary and within the hand they don't. So in general, if I take this finger and that finger, this finger and that finger, likely they will covary. Unless I'm very unlucky.
What I'm asking about is whether there is this hierarchy. For example, if you put these 4 fingers repeatedly, whether you can say by looking at the data that the fingers belong to the left hand, how they belong to the right hand.
I think that the answer is yes. I think that if we do the analysis with crossed pairs of fingers, we will find weaker, significantly weaker covariation as compared to fingers within a hand. I think we even tried it, but we never published it because we thought that was somewhat crazy. The analysis was somewhat crazy. But yeah, we tried it.
Mark, you have defined the concept of synergy, and it's not a problem here. And in the lab, we like this concept to describe the muscular coordination. But what is your opinion on the debate of the existence of synergy as a unit of control?
I don't think. I mean, before debating, we have to define words. Now, if synergies are defined as a bunch of variables which scale together, then I think that this debate is a little bit empty because it's very task specific. Some variables, some muscle activations tend to scale together across a broader range of tasks, some are not. Because the fact that we have so many muscles is not to make life harder. It's just to make the motor repertoire broader. So obviously I can organize my muscles into groups that will scale together within some kind of group of tasks that are similar, like swaying or stepping. But if I try to use muscle activations during kicking a football, I'm pretty sure that all the so-called synergies will reorganize quite dramatically. I think partly also these covariations of EMG patterns, because the brain doesn't manipulate EMGs, it manipulates referent configurations. So if I want, what kind of typical changes in referent configuration? This one, for example, as compared to vertical standing. So if my referent configuration is this, but my actual configuration is that, then I will have activation of my ventral muscles throughout everywhere trying to move me there. That's synergy or muscle mode number 1. If my referent configuration is backwards, dorsal muscles. And now there may be a more complex referent configuration because with Tomarober in particular we performed a study when people were asked to produce a very unusual task, which was producing a pulse of shear force without shifting center of pressure. It's very tough to do. Well, you cannot produce a large amount of shear force because you'll fly out of the lab. So it has to be balanced quickly by the force in the opposite direction. So we asked, it was kind of a very strange motion like that when shear force changed quickly in a pulse way. Now, when we analyzed there and we recorded muscle modes, they corresponded to this type of postures. So not this type of reference configuration, but this. So I think that this consistency in muscle activation patterns that are seen in modes is simply a reflection of learned changes in referent body configuration across more or less standard tasks. And our standard tasks during standing are stepping, swaying, maybe, not much else. Everything else is quite unusual. I mean, we can do a very quick turn, for example. If you ask a person to do a very quick turn and you look at the muscle activation patterns, you'll find something completely different from regular so-called synergies that are being described. So I think that the utility of this language of synergies is very task-specific. Within a certain class of tasks, they allow you to reduce the description of the data from, I don't know, 16 variables to 4 variables, which is nice, certainly because it's easier to deal with 4 variables than with 16. But I don't think that it moves us closer to the understanding of how it actually works. It's more like useful language for the description of the data. So I don't have much of an argument with this approach. So I think it's useful within its realm of applicability. But one should understand that even if you ask a person to stand on a board with a narrow support, like balancing like that, all the synergies change. Because a lot of co-contraction appears, for example. Because typically in synergies there is not much co-contraction during natural movement, because antagonist muscles are usually activated in a reciprocal fashion. But if you put a person on an unstable or precarious position, there's a lot of co-contraction, and so the composition of this muscle modes changes. It also changes with practice.
Your opinion is clear.
Well, my opinion is that for us, we identify these synergies, but for us it's the first step in the analysis. For us, synergies are elemental variables for further, modes are elemental variables for further analysis of synergies, which are kind of functionally important, which relates to stability of performance, stability of some potentially important physical variables, mechanical variables.
Okay, thank you, Mark, and thank you for...
Thank you very much. Thanks.